What we're going to be looking at here is a quadratic function here where we're going to be calculating the eigenvalues here in our eigenvectors. So we're going to start out with this quadratic function here where we got some x squared, y squared, and z terms here times some coefficients. And along with it, we're going to have some cross terms here, yz, xz, and xy here. Then we have this lone term here, minus 294. But what we do here with these eigenvalues and vectors, we can eliminate these cross terms here, and we're going to end up with a new function here, a quadratic function. It's going to have the x squared, y squared, z terms plus that lone term here. But we're going to have eliminated the cross terms. But by doing so, we're going to come up with new coefficients here for our x, y, and z squared terms here. So pictorially what we're looking at here, we start out with this function here where we show the x, y, and z axis here, and they're really canted off here at some angles here. And along with it, the quadratic function we have here is canted off too. It's not it's symmetric to these axes here, but it's canted off. And what we're doing here by calculating our eigenvalues and vectors, we can come up with a new function here. We can define that quadratic function here with our just x, y, and z squared terms here, and everything becomes, our function here becomes nice and squared up here for x, y, and z axis compared to what we had over here when we started out with our original function. And what we're doing here as far as eigenvectors here, just going down and looking at it, we have really three of them in this case here defined by our x, y, and z coordinates here. So we have this eigenplane here, and we have two vectors here, and they're really 90 degrees apart for our function. And we also have our third one here, this green vector here, and that's 90 degrees perpendicular to the red and blue, or the eigenplane here. And what we're doing here when we come up with our new eigenvalues here, what we're doing here is we're rotating those eigenvectors as well here up to, really, you're going to be equal to 1 here. Where over here the eigenvectors here have a less than 1 value, like 0.6, 0.7, 0.8, and so forth. But what we do is we just rotate all three of those vectors up here to come up with our new eigenvectors here of a unit of 1, and there is some degrees of rotation here, x, y, and z here. So this is what we're going to be looking at. Okay, so the first thing, let's go and let's calculate our eigenvalues. Okay, so the key here is you have to set up a symmetric matrix or square matrix based on your original function that you're working with, this quadratic function where these squared terms, x squared, y squared, and z terms. And first, let's look at the matrix that we have to set up, and then we'll look at that. So we have a matrix here. It's really a 4 by 4 matrix here. X, y, z, and 1 here. Those are define each of our columns here, because we're dealing with x, y, and z here in our quadratic function, along with that unit here of minus 294, or what we define here as 1. Okay, so those we define across our columns here, across our top for our matrix, and along our rows here, along our sides, representing each row here, you're going to have x, y, z, and 1. Okay, so that's what you have to do. So let's fill up our matrix here now. So we'll set up, looking at our x, all these lone terms here are squared terms, x, y, and z squared. They become sit on the diagonal of our matrix here. Okay, just so you understand that. So let's look at it. 103 here for x, so we got x here at 103, and that's our column, and then a row here. X is 103. And then same for the y. Y squared here would be 125, so you have your y column, y row. It sits on there. And then 66 here for z squared. Z column, z row sits in that position. And then you also have that lone term here, minus 294. That sits in our unit column here of 1. Column 1, row 1. But the key is to get rid of these, we have to set up these cross terms here. So this is where you're going to set them up in the upper and lower triangle. You make this matrix square here. So let's just look at it here. 60 yz, that's a minus 60 here. So what would that go? So you got to go for yz. So you're going to have z, y here. Half of the minus 60 is minus 30. Z column, row y. And then the other half goes in the lower part of the matrix here. Y, z, y column, row z. So you see what's going on, minus 30, split in half. And then for the minus 12, xz, same thing here. Where would we set? Oh, z in x we're talking about. Minus 6, half goes into z, x here, and then the other half goes into X column row Z. So you can see how they balance each other out. And then 48xy, that's sitting here, what? Y, X minus 24 again. And then the other one would be where it's sitting here, X, Y, column X, row Y. So you see what's going on, minus 24. And then again, that lone term, minus 294, sitting in here in the column 1, row 1 here. Okay, so the next thing you have to do here, and you're using a computer algebra system here, I'm using MapleSoft, what you have to do is you have to take, and you take your, in this case, I say it's I2 here, but it's really matrix, your matrix here that you set up, your symmetric matrix, and then you subtract from it, you add in this lambda term, or some variable you landed in it, put it in here. I'm just using the symbol lambda because that's generally what they use, and you take that times the identity matrix here, 4 by 4. So what are we talking about? The identity matrix here is 4 rows, 4 columns. It matches our symmetric matrix over here, only that we've got along our diagonals we have 1 here, and all the other entries here are 0. Okay, so that's our identity matrix. So you take that, you take your matrix here, subtract from it lambda times the identity matrix here, and essentially what you come up with, just to understand what's going on, this matrix here, all you've done is you've added this lambda term across your diagonals, and you're subtracting it in this case, subtracting it across your diagonals. That's the only thing that changes between this matrix and this matrix here. Okay, but that's how you come up with it, using the identity matrix here. Okay, and then the other thing is, now that you have your matrix set up here, then you just take the determinant. You'll have some function called out here in your software as a determinant of your matrix here. Determinant of this matrix, AA, you set it equal to 0, and then what you solve for is you come up with this characteristic equation here, where you're going to have that lambda term sitting in here. You're going to have some lone term here and a lambda term x squared times a coefficient here. Then you're going to have a single lambda here raised to the power 1 times some coefficient, and then plus lambda to the 4th. That's all set equal to 0. You factor everything out here, and then you come up with your eigenvalues here. Lambda plus lambda here is showing either subtracting or adding your different eigenvalues here. You just solve for that, and essentially you're just your minuses become pluses, pluses become minuses, shown here. Minus 294 here. Lambda is equal minus 294, 147, 98, and 49. Those are your eigenvalues. And then you would call out eigenvectors here. And this is what we're going to look at, how we go and calculate them using our computer system here. But you could just call them out. You're going to have, for each one of those eigenvalues, you're going to have a set of vectors here, x, y, z, on your axis, and then you have that unit of 1 here. But this is the case here where these eigenvectors are mature eigenvalues, but they have a unit less than 1, like 0.429 here, minus 0.875, and then 0.286 here. And all of them are less than a unit of 1. But what we're going to look at is how we bring these into a unit of equal to 1 here. Okay, so next let's go in and we'll look at how we do some calculations here, manipulations here, to come up with how our eigenvalues and eigenvectors work together. Okay, now we'll calculate our eigenvectors here and also our eigenvalues in terms of the coordinates, or their 3D space here in our XYZ coordinate system that we're dealing with. So we start out with our symmetric matrix here, and you're going to really be using some computer algebra system here. I'm using MapleSoft for this example. So we start out with symmetric matrix here, and we also have our identity matrix here, 1s across the diagonals here, 4 by 4 matrix to match our symmetric matrix. And there we would have calculated our eigenvalues here, which we've previously done. Now we have to come up with our basis, or eigenvector XYZ coordinates, and then we know those, then we can calculate our eigenvalue XYZ coordinates in space. So for first thing you do here to calculate your XYZ coordinates, your basis for your eigenvectors here, you're going to have some call out here, a null space call out, or some call out here in your computer algebra system, and that would be based on taking A, your symmetric matrix here. I got it called A2, but it's really A here, your symmetric matrix, and you subtract from it the eigenvalue here, each one of those eigenvalues times the identity matrix, and it would have been set to 0 or something, and it would have given you the eigenbasis here for each one of those eigenvalues here, what I mean by the XYZ basis here. And then to calculate your eigenbasis, or based on your eigen position here for your XYZ coordinates for your eigenvalues, what you would do here is you take the basis you have calculated here for each of your eigenvectors here. And what you would do here, well, you have your basis here, and then the call, this is just the way MapleSoft does it. They get the basis here, then it gives you an eigenvalue. But the key here is a dot product to calculate the basis or your XYZ coordinates for your eigenvalues. You take the A, your symmetric matrix here, let's just call it A, dot product times your eigenbasis that you calculated for each one of those eigenvectors here. Dot product A matrix here times your eigenvectors basis here. And that's going to give you your XYZ coordinates here for your eigenvalues. Okay, so just laying them out here, you can see the eigenvectors. They've got a plane here, and then you got your red and blue one here sitting on the plane, and then your third eigenvector here is sitting as this green one here. And that, remember, was 90 degrees perpendicular to your plane here. And same thing for your eigenvalues here. And the eigenvectors really give us the direction. They set our direction here of our coordinates. The eigenvalues here are the magnitude of our coordinates. So these eigenvectors here are going to be just the eigenvalues are just a multiple of our eigenvectors here. And let's go look at what we would have calculated here with that dot product here of our symmetric matrix times the eigenbase, or the basis XYZ coordinates for each one of the eigenvectors. Okay, so what we would have done here, the computer system, or the computer algebra system, would have given you something like, here's your vector. I'm showing X, Y, and Z coordinates here for the rows. And just take a look at, and then you would have had your eigenvalue. And based on that, your XYZ coordinates here for your eigenvector times your eigenvalue here. This is, or you're going to get the position vector here for all those eigenvalues, or their XYZ coordinates. So just understand what's going on here. So if you had to do this by hand here, and you knew what your eigenvector, your unit amounts here for your eigenvectors, let's just say your the first X coordinate here is 0.429 here. You take that times your eigenvalue. In this case, it represents the 147, the eigenvalue here. And that multiple is going to give you the position here for your eigenvalue here. And your X position, 0.429 times 147, gives you a value here of 63. Okay, so that's how you calculate your eigenvalue position here in your XYZ coordinates and magnitude. And just carrying on here, just looking at Y position, say it had a minus 0.857 times 147, that's going to give you a minus 126 here for the Y position here in eigenvalue. And then your Z position, 0.286 times 147, is going to give you this 0.286 here. Remember, all these are your vectors here. Here's your eigenvalue, and here is the coordinate value for your eigenvalues. And so you got, in this case, 0.286 times 147 is giving you 142. And the same thing for each one of it. The computer program would have given you the vector position here, unit vector position here for your vector, times your coordinate, and then it has a coordinate here, and then that multiple here, vector X times your eigenvalue here gives you your vector position here for your eigenvalue, X, Y, and Z. So you would have done that for, in this case, we had 98 here for eigenvalue, and then for that 49 here for eigenvalue. Again, here's your vector position, X, Y, Z. Times your eigenvalue gives you your eigenvalue, X, Y, Z position. And that's before the rotation. So if you look here, all your eigenvectors are all less than a unit of 1 here. You can see it. There's all a decimal point less than a unit of 1. But your eigenvalues, again, are just calculated as a multiple of that unit vector times the eigenvalue gives you your position. Okay, so this is all before the rotation. So let's go and let's look at what we do here to just prove out what we're working with. Okay, so starting with another matrix here. I've set it up, a 4x4 matrix. In this case, this is based on our eigenvalues here. Diagonal of our eigenvalues are shown across the diagonal of our matrix. All the other rows and columns here have 0 entries here. Okay, and then we just have our square matrix here, our identity matrix with our rows of ones across our diagonal here. So just again, for a characteristic polynomial, all you do is take the determinant here of the A matrix, and just remember this A matrix just involves our eigenvalues at this point, and then you subtract from it, and you have a lambda on here. I'm just using x in this case here, times your identity matrix. So you would have solved that here, and you would have come up with you would have come up with your eigenvalues that we essentially have here in our matrix that we have here. So those are our eigenvalues here, just to see it worked out okay. Minus 294. Minus, or 49 here, 98, 147. And everything, remember, the rows and columns match. X, 147 times x here. That would be an x squared, and so forth. Okay, so we've just proven that out here. So now to come up with our basis here, our new basis here for our eigenvectors. Again, we'd have some call out here as a null space, and then you'd have your eigenvalues here, this matrix here, this A matrix here, with the diagonal matrix here, with the eigenvalues on the diagonal. Subtract from it the eigenvalues, put each one of those eigenvalues in here, times the identity matrix. And we solve that here, setting it, I guess, equal to 0 here. You're going to come up with the basis, or the x, y, z coordinates here, for each one of the eigenvalues here, with that null space call out. So you're going to come up with your, again, you're going to have your basis here, your eigenvalues. Basis would be the x, y, z coordinates here for those eigenvectors here. That's the basis we're talking about, x, y, z, and also that one value here. Eigenvalues, and then again, same thing, just do the dot product, your eigenmatrix here, or eigenvalue matrix here, the diagonal matrix here, subtract dot product times your eigenbasis, the basis here, or those x, y, z coordinates for each one of the eigenvectors here. That dot product here, and this is what's going to happen here after the rotation here. So before the rotation, when we calculated our position here for the eigenvalues, that would have been the magnitude position, and then our eigenvectors would be the direction of each one of those eigenvalues here. So what we've essentially done, we're going to rotate this entire set of eigenvector values here up by a certain amount here, by a certain amount. We'll prove out what we've done here, and those are just the x, y coordinates. Eigenvectors, the same thing. We've rotated them up here a certain amount here. Each one, just the whole system, all three vectors got rotated up a certain amount here. Okay, so let's go and let's just prove out what we're talking about here. Okay, so again, just looking at this, here's our x, y, z position here for our vector here, and based on our eigenvalue here. And then this is the vector position here. And say we got the x, y, z coordinates. Now everything here, our eigenvectors here are a unit to 1 here, based on that calculation here for our eigenvalues. So here, x position, it has no y, and z position, nothing in z. So everything is sitting on that x-axis here, and it happens to be the eigenvector value here, or eigenvalue here of 147. So taking 1 times 147 gives us the position here for our eigenvector here, that eigenvalue, excuse me, the eigenvalue position here. So that's what we've done here by the rotation. We've gotten rid of our, everything comes out, eigenvectors are now all a unit of 1 here. Look at it, this case here for this first eigenvector, 147. And then for the next one here, that 98, eigenvector here, 98, its position here is 1 here for the y position. First one is 1 here for the x position, 1 here for the y position, a unit of 1. The x and z, and then the unit of 1 here, have 0 position. Take that times our eigenvalue here of 98. That's going to give you your eigenvalue position here for your eigenvalue position here, 98. So nothing in the x, nothing in the z, it's all in the y position. And same thing for your last position, eigenvalue here, 49. Nothing, here it's 0, 0 in the x and y, and it's sitting here in a unit of 1 here in your z position. So here's your eigenvalue of 49 times unit of 1 here, z position, gives you a unit here in your z direction here at 49. Okay, not to confuse everything, but this is essentially what's going on here. By doing coming up with our eigenvalues here, our eigenvector is going up, and everything's being rotated up here by to get it up to a unit of 1 here. And just remember, the eigenvectors here give us our direction, eigenvalues here give us our magnitude. So just looking again here for eigenvector here with a position x1, y, and z0, we had that was 147, and that gave us a position here in the x here in our eigenvector here of 147. Okay, so just looking at it in these terms here, so if we go up here and just look at what we're talking about. So before the rotation, this was our polynomial that we're talking, our quadratic function, our ellipsoid here, and you can see our axes were sitting off here. And this is the case here where those our eigenvectors had a unit here of less than, have a decimal point less than 1 here for the x and y and z coordinate positions here. Those are the eigenvalues. And then after the rotation, this is what we came up with. Now, this is, I'm not pointing it all out here, but we talked about that with our vectors and our values. For our x, z, and y values here, for each one of those vectors, they're either landing here on our y-axis, our x-axis, or our z-axis, because in this case, and then we also have that minus 291. But nonetheless, you can see how it's straightened itself out here. So that's what we're talking about here when we're talking about eigenvalues and eigenvectors, and looking at it specifically in the direction and how we were able to transform this polynomial or this quadratic function here by getting rid of the cross terms here and coming up with a nice clean function here where it's very symmetric and very easy to understand here. Okay, so that'll end our discussion.